मैं भी LMS पे ऐड नहीं हूँ तो मुझे पता नहीं 21 रोस्टर में लेकिन 21 पे आते हैं
So 21.
21? So everybody's here, fine. Okay, so basically, this is the first time ever that I'm teaching this course and I have no idea what I'm doing. So, this is going to be an experience. Let's see. So, I mean, I've looked at so many books and still I couldn't sort of settle on one. So there are different books and each has its own merits and demerits. Some are written very well, or mathematics is just too difficult. I mean, the best book that you could ever hope for to read in quantum field theory is Weinberg's 3 volumes. Okay, it's just damn difficult at this level. I mean, that is not simply an undergraduate book. And so I was looking for a book for undergraduates. And so I've settled for these 2 books. This basically is sort of an easy book, but also not very wordy and not sort of difficult to sort of read. But I mean, if you combine it with the lecture notes, then I think you should be able to get through it. I mean, this is another very good book, but slightly different sort of outlook to the course. But anyhow, so we're going to just sort of take these 2 books and run with them. This is Mendel and Shaw, Quantum Field Theory, and this is the same title by Srednicki, Mark Srednicki. And so then there is another excellent book by Major, but as I said, every book has its own sort of challenges. So you need to know group theory, the groups, different algebra, Lorentz group, and representation theory, a little bit of representation theory before we can do that. So, so we're not going to do all of that. And there's going to be a little bit of relativistic quantum mechanics in the mix as well, for example, when we derive. Since we're not going to go that Major's way, representation way, so we'll have to derive the Dirac equation like Dirac did. And then we're going to sort of talk about invariance and then the Lagrangian and stuff, instead of going from representations to invariance to Lagrangian to equation. So anyhow, another good book for relativistic quantum field theory is Sakurai, advanced quantum mechanics. Yeah. No, there's a modern quantum mechanics and then there's advanced quantum mechanics. So I'm talking about advanced quantum mechanics. Okay, so anyhow, so basically notes on these 2 books, and basically, if you guys are not sure, you can just ask. For example, this lecture, the first couple of lectures are going to be the first chapter of Mendel and Shaw, and as usual, I will have to provide some of the missing steps in there. Anyhow. There are other differences in the books, and so I'll mention them as we go along. The most difference that you're going to see in this course is that initially the grading was set up as that there was no homework, and I mean there will be homework given, but it will not be collected and graded. And basically there will be a lot, something like every other week there's going to be a quiz. Or maybe every week or whatever suits Junaid or whatever. So and the quizzes are going to be directly from the homework or very closely related. And so and then there was I had kept a presentation, and then now you see the number of students here. We possibly couldn't have presentations in any meaningful way at the end of the course, so I've sort of taken them out, and instead there's a midterm now. And so there are quizzes, midterm, and final. That's it. Some of the other stuff is also mentioned in the course outline, and I'll ask Junaid later to upload that as well. You guys don't have that, right? No. Okay. So before I talk about prerequisites, or maybe I should talk about prerequisites first. Yeah, let's talk about prerequisites first. So I'm going to be expecting that you know special relativity, right? Especially things like 4 vectors and tensors, okay? And transformation laws and Lorentz transformations and all of the other ideas related to special relativity, okay? So for example, I'll not be explaining anything like what J-mu is, or for that matter, for example, in this course, this and this would mean the same, right? In GR, you know that these are the components and these are vectors, and so yes, another thing remind me to mention about this signature of the metric. And so I'm not going to be explaining what this thing is. For example, you just need to know. And if we change frames, how they transform. Then there are things like core velocity, right? You just need to know what core velocity, for example, is in different frames. I'm doing, by the way, some of the tensor, not the tensor algebra, but tensor calculus in GR. And so people who are interested can come to the first few classes in GR. It's up to you. Then I'll be assuming that you also sort of know a little bit of classical field theory, something like you know what Lagrangian is. So, for example, I would expect that you know that the action is sort of, this is the Lagrangian density, and so if you were to integrate that over the whole space in a region, you get the action, right? If you vary that, where this Lagrangian is, in our case, is going to be a function of fields and their derivatives, right? And so, and if you vary that and ask this to be stationary for the classical configuration of fields, then it tells you that this thing is equal to partial by partial u phi. So, for example, yes. So, for example, you need to know what this is, right? Does everybody know what this is? Fakir? Yes. Fakir, do you know what this is? Right? So d mu is just d by dx mu. This is a short for that, right? So there are other shorts that we use. For example, phi common u or mu. This is the same as d mu phi, which is the same as this, right? What else? Okay, so for example, an example would be for example, this Lagrangian density, right? And if you were to apply Euler Lagrange equations to this Lagrangian, it will tell you that that this field obeys this equation of motion. Okay? And so, what does it mean to say that this it obeys this equation of motion?
The Euler-Lagrange equation is satisfied.
What does it mean? What is the field? Euler-Lagrange equation is satisfied. For example, then we say that the rate of change of momentum is equal to the force. It's satisfied. What does it mean?
If you know the field at one particular time, you can predict it at given time. Using the equation of motion.
But we're not talking about prediction. What it means is that field is given in the space-time. Not just space, it's given in the space-time. And at every event, so it's a local statement, at every event, this equation is satisfied. The field at that event satisfies this equation. Right? That's what it means. Right? It's different from what it means for a particle. Right? Where time is just at a given point where the particle is, locally the derivatives mean that. So this is the field. Right? And so we've talked about that in the course of RED. And basically, I'm not going to be repeating anything that we did in that course. That's one thing. And so, for example, you also. So I'll be talking about the energy momentum tensor a little bit, and I'll talk about the Euler theorem. But I haven't talked about the energy momentum tensor. So, is this correct? That's right? Should be something like this, right?
Yes.
So anyhow, we show that you have a tensor, a particular tensor, like this, such that all of the conserved quantities, these are conserved quantities. So for example, all of these quantities are conserved. For example, P0 is the energy, and so this is the energy density. Things like these. So I will have a chance to, for example, talk about these when I talk about Euler's theorem, but not things like these, right? So I will be expecting that you know them. Then another example of this, not being repeating, would be that the Lagrangian for the electromagnetic field is some constant f mu nu. This constant would depend on which system of units you're working in, right? And so if you were to apply that, okay, so f mu nu, for example, can be defined like this: Fi0 is Ei, and Fij, where this is the electric field, okay, and so this is epsilon ij k vk, and this is magnetic. And so if you want this thing is in a frame. This thing is, by the way, this thing is going to be easier, and this was B2, B3, B2, and B1, right? And so this is minus. B minus it? Something like this, and this would be with a negative sign, B2 and minus B1, something like this. Maybe you can check it out, or work it out from there. Okay, so I will not be talking about things like these, right? And another thing, for example, A, U, which are the potentials, they can be written as phi and A. And in terms of these, you know that the magnetic field can be written as del cross A in 3 notation, and the electric field can be written as minus del phi minus partial by partial t. So if you vary this action according to that Euler-Lagrange equation, if you vary that action and ask the variation to be stationary, then what you get is this. This is the equation of motion. And so basically these are Maxwell's equations. So del dot E is equal to 0, del dot P is equal to 0, del cross E minus partial B by partial T. There's a minus in here, right? And del cross B is partial B by partial T. And if you use this, you can write F Q mu as d mu A mu minus d mu A mu. Right? And
the last equations,
second,
for the last equation we derived, you can't quite.
not the last two equation. Trying to think this and this.
Yes.
Yes. They have to come from the Bianchi identity. Right. So what he's saying is that if you define F mu like this, there is another equation that is automatically satisfied, which is this. Okay. And and if you're working in a Lorentz gauge, then this equation basically reduces to box A mu is equal to 0, where box is just d mu d mu. So Laplacian, for Laplacian. Okay. So all of this, for example, is assume that you know. Then a little bit of Fourier analysis, right? Any questions? Questions, guys?
सर इसको रिव्यू करने के लिए ग्रिफिथ काफ़ी हमने तो ऑलरेडी आपसे लेकिन हमने पढ़ा हुआ है तो रिव्यू
हाँ, अगर आप ग्रिफिथ्स का लास्ट चैप्टर कर लें, डायनामिक्स छोड़ दें, उससे आगे जहाँ से फील्ड टेंसर शुरू होता है वहाँ से कर लें तो that should be enough, right? Otherwise, you can have the notes that I gave these guys. Okay. Then on the quantum side, you need to know perturbation theory. So all of perturbation theory will be assumed. Okay. So quantum mechanics too. Right. So apart from her, is there anybody else who's done QM2? Done. Not done QM2. Is there anyone who has not done QM2? Okay, everybody's done QM2, so that shouldn't be a problem. You guys have done QM2, right? No, you guys. Of course you guys. Which part are you from? You were a computer scientist, right?
No, engineer, mechanical engineer.
Mechanical engineer. Okay, so okay, so today I'm not going to sort of do anything more than review a couple of things. For example, I'm going to review, let's say, quantum mechanics 1, a topic from quantum mechanics 1, which is simple harmonic oscillator, just to remind you guys that you really absolutely need to know that topic inside and out. So whatever I mentioned, and whatever I'm going to mention now, you just, if you're sort of not comfortable with any of that stuff, you just come home and before the next class, you just sort of brush up on that. Okay. if there are any if there is a large part of the class that needs sort of reminding on some of this stuff, then we can arrange a tutorial. For example, I was thinking that if you guys need it, we could arrange a tutorial on classical field theory, like just the Klein-Gordon equation maybe, and then. What do you mean yes? You guys. Looks out of me, or am I talking? Yes, I was really talking to you guys in the back, because you guys, I'm not sure if you guys have had that. I'm not sure if you guys have had that. 1, 2, how many, and 3.
Scalar field.
कहाँ से पढ़ी हुई है? तुमने एडवांस पढ़ी मैकेनिक्स पढ़ी है तुमने? तो कहाँ से पढ़ा है? टाइम वगैरह कोई वगैरह पढ़ी है? हाँ, तुम लोगों ने पार्टी
नहीं, हमने कॉस्मोलॉजी में ये स्केलर फील्ड का लैग्रांजियन लिख के उसके साथ काम किया हुआ है। मतलब Klein-Gordon इक्वेशन में पढ़ी है, हमने एटॉमिक में पढ़ी थी।
अच्छा, तुमने इन्फ्लेशन में
जी, इन्फ्लेशन में।
हाँ, ठीक है। Okay, anyhow, so can somebody remind me? By the way, just like these vectors keep on appearing over and over and over again in more and more and more abstract form, right? And the same is true for simple harmonic oscillator. This keeps on reappearing over and over and over again, more and more and more abstract form. Okay, so can somebody remind me what the Hamiltonian is?
V squared over 2 plus half and omega squared.
Right? V squared over 2 plus right? And so what you can do is that attack this problem, that is solving time-independent Schrodinger equation. You can attack that problem in the Schrodinger representation. And convert this into a differential equation, and then just try to solve it. But you guys have seen that a far better approach is to work in energy basis. So Q, P is IH step. So this is your quantization condition. Right? So what happens is that you define these operators, right? And there's 2H cut and omega, and then you have m omega q plus IP, and then you define a dagger, which is 1 over h dot m omega q minus and then what? And you show that A with A dagger is 1. And using this, you can write H as H cut omega over 2 H cut omega A dagger A. This is called the number operator, right? And so this becomes n plus a half, and basically you can show that if you have an eigenstate of H, then A on that state is also an eigenstate of H with slightly less energy, which is exactly H cut omega, right? And so you have a ladder of states. There is the lowest possible state, which is annihilated by this operator, right? And hence the annihilation operator. and basically this is the vacuum, right? This does not have any of the quantas. So this thing, this operator, sort of creates a quanta, and so this is, let's say, 1. Right? And so you have this ladder of states. So you have 1 and 2, and the difference between, energy difference between each one of those is H calculated. And so a general state N can be written so if you assume that this thing is 1, this thing is normalized, then you can write a normalized nth state by the repeated application of this operator n time on 0, and this is the normalization, which makes it 1. Questions? So these are eigenstates of H and N. So this thing is going to be En, N, and N on this is going to be N on N, where En is just N plus a half. So you guys remember all of this? And so if you apply A on N, it gives you N minus 1. And of course, there's a square root of N. And if you apply A dagger on N, it gives you N plus a half. N plus square root. So and hence the annihilation operator, because the energy, one quanta of energy is annihilated, and the creation operator, one quanta of energy is created. So all of this is in the Schrodinger picture, right? What about in the Heisenberg picture? The operators become time dependent. And how do you calculate the time dependence of the operators? Yeah. So, for example, in the Heisenberg picture, so this is the equation, and you know what this thing is because you can calculate that, and so this is plus A squared over A. And so dA over dt is minus I1 over A, and hence the time dependence of A can be given questions? Okay, another review. If you have any field, right? So if you have any field, let's say, in order to be concrete, let's take this, where is it? This field, this as a field. This as a field, okay? So if you have any field, right? So it's going to be a function of space and time, right? And by the way, although later on we're going to be sort of, in some sense, fully relativistic, you can talk about non-relativistic quantum mechanics in terms of fields. Okay? And in fact, I'm going to do a little demonstration of that in the next class. That you can, it's just another way of doing quantum mechanics, right? But it has some advantages over non-relativistic quantum mechanics. Well, non-relativistic quantum mechanics has some advantages over field theory point of view. But there are some other things that we simply cannot deal within the framework of non-relativistic quantum mechanics, like the creation of particles. Okay. But this is just another way of doing quantum mechanics, right? And so, for example, I'm not sort of writing it in a fully covariant notation. So I'm taking space and time separately. Right? So you can think of this as a field at a given time, in 3 space at a given time, right? Okay. So so I can always sort of write that as d3k a of k t, right? U to the I x. So this is in the k space, which is the momentum space basically. So p is h cut k or whatever. We will be always sort of transforming our fields like this and then working with each mode separately. Because where you have a differential equation, in the k space you have an algebraic equation. And all modes are decoupled. And so you can talk about different modes. Okay? And so this will become sort of very clear as we go through the course. But I'm just reminding you that these are kind of things that you need to know. So if you're sort of are slightly concerned with what I'm saying, and just go back, pick up, I don't know, which book do you like? Physics? Talk about Fourier transforms very well. I mean, just go through some of the exercises. You need to know some of the formulas. For example, there are things which become delta functions and stuff. You need to know them, stuff like that. And so, by the way, so you can write every field like that. For example, if you have a scalar field, this and this will not change, but this will. Right? In this case, this is a vector. So you have a vector on the left-hand side, so you have to have a vector on the right-hand side, and so this is a vector. And if you were to have a scalar here, you would become a scalar. If you were to have a spinner here, this would become a spinner. Right? Okay. Okay, now, so if this is, let's say, the vector potential, then in Coulomb gate we know that this is divergenceless. And in the K space, this equation becomes very simple. It just says that K dot A is 0, right? Which means that A is only a sort of have 2 degrees of freedom. And those 2 degrees of freedom can be sort of identified with the 2 polarizations of the field. Okay? And so, basically, there are these 2 polarization vectors, let's say epsilon 1, epsilon 2, and then there is the sort of the k vector. And so this k vector, k over k, this forms an orthonormal basis for it. Okay? And so this is just a linear combination of these 2 vectors, because k dot A is 0. Right? So this, and this. One and this. And so this thing is going to be some epsilon r, right? And which is going to be bound by k, and some a of k t. Yeah.
I didn't understand anything you said about that.
Which equation? This one?
How you can see this part?
This one? The whole thing. That's just a Fourier transform. Just a Fourier transform.
What did you say about it?
I don't know. What did I say about it?
About the, like,
I said a lot of things. Once again?
It's not out of the KV.
Oh, if this were the scalar of the vector potential, then del dot A is 0, right? So del dot A, when you apply it, where does it go? Here. This is the function of K and T. So this del dot this will give you that K dot A is 0. Okay. Yeah. Okay. Now there's a difference between. Let me erase this out. So now there's a difference between the two books that I've mentioned. So you can either sort of work with so the number of degrees of freedom. What is the number of degrees of freedom in a field, for example? You have one value at every point, right? And so so you have a continuously infinite number of degrees of freedom, right? And so this is given by the fact that this is continuous too, right? On the other hand, if you were to put the field in a box and apply the periodic boundary conditions, you can convert that integral into a sum, which is easier to deal with, right? And so that's what Mendel and Shaw has. But Sarniki doesn't do that. Okay. And so, by the way, you can use any of the two things, gives exactly the same result. And in fact, we might be going in some of the formulas that when we're doing calculations, sometimes it's just easier to do the integration than to do the sum. And sometimes it's just easier to do the sum than the integration. And so we'll be using both of them. So the conversion is that 1 over V. So basically, so if I were to put this in a, let's say in a box of side, let's say L, right? So the volume is at Q, and apply the boundary conditions at A, 0, X, Y, Z, T is A, L, Y, Z, T, right? Then you know, as you know from your experience from particle in a box, that the number of K values are countable now, right? And so K can only be 2 pi over L, 2 pi over L, N1, N2, N3, where these could be any number between 0 plus minus 1 plus minus 2 infinity. Okay, so n's are 0 plus minus 1 plus minus 2. So in that case, this integral can be written as a sum, and so 1 over 2 pi cubed integral d3k. This is just sum over k, k 1 over v. Now these are the total number of what? Modes, which is total number of states, energy states that are possible, total number of states that are possible. And 1 over v just tells you that this is the density of states, which is the same thing over here. Okay? And so you can convert this into a sum. So if I were to convert this into a sum, I can write it like this. So for example, A, X, T. So there is, okay, so there is going to be a vector, polarization vector, right? K, right? This is a vector. And then there's going to be an A, K. This is the coefficient or the amplitude of this particular mode in the expansion of this field. Right? Okay?
So can you explain again what this is?
This is the same thing as that. Except I've sort of broken this down into these two. This is the vector, this gives you the direction, and these are the two sort of components. Right? And then there's a sum over R. Right? And then e to the I. And then I'm going to put, and I'm going to tell you, so in Manning and Shaw, he keeps C, so most of the time I'll just take C to be equal to 1. Okay? So anyhow, so the coefficient that he puts in front is this. And all of this will become clear later on why exactly this coefficient has to do with the rotation plus the Lorentz invariance and blah blah dimensions and Lorentz invariance and I mean you can either work things out and then realize what this thing is and then come back and change it, or you can just start with this one. Okay, and now of course, you have to have a sum over K. Right? All possible modes. But this field is real. Right? The potential is real. Right? So, one of the ways to deal with that, I mean, in general, this is a complex quantity. So, one of the ways is that you say that I'm just going to take the real part of that. Or, the same thing is saying that I'm going to add the complex conjugate. And so this is going to become AR star e to the minus I e dot x. So, I mean, you could have sort of done this thing as well. So, written D3K over 2 pi cube omega k, and then epsilon r, the rest of them is the same. So you can either written this or that. Same thing. Okay? What we're going to do is that we're going to work with this as much as we can, and sometimes for the calculations we'll go to this. Questions? So all possible value of k and r, if you want, r is equal to 1 over 2. So there are only two possible polarizations. So these are the sort of these will become the polarizations of the photon. They are going to be quantized. Questions? Gamma? Yes, you can say that all of that is in here. All of that is in here. What is important is that later on when you, for example, calculate the energy, it has to come out. These potentials are not observables. The energy is an observable. Questions? Okay. Okay, last thing. Now, what is the time dependence of this thing, for example? We know that box of A is 0. Right? Where does it come from? Why is box of A 0? Yeah, it's in a particular gauge. If we're working in Lorentz gauge, then you can show that, for example, phi is 0 and A satisfies this equation. Okay? Anyhow, so if you have an equation like this, you can determine the time dependence of these coefficients. Okay? So let's do that. So this equation means if you're keeping C for the time being, 1 over C squared, partial squared A over partial T squared, this is going to be equal to del squared A, right? And so del squared A is basically minus K squared A, right? Del just becomes K. So differential equations on the other side, in the K space, just become algebraic equations. And of course, there is a sum over K somewhere. By the way, this is this object in the whole glory. So sometimes there's sum over K, there's sum over R, blah blah blah, and so if you want, you can sum over K and R. Sometimes you just clumsy a little bit. Anyhow, so if you open this side up, this tells you, let's call this whole thing alpha. So this says alpha, sum over K, epsilon R, and this is a function of K, I'm not writing it. And so partial square A over partial T squared e to the I K dot X plus complex conjugate, right? Right? So this thing is equal to sum over K epsilon R omega K squared A e to the minus I K dot X. There's a minus sign. And where does this minus sign come from?
iota do
Yeah, iota to the phi का नीचे. That gives you a minus sign, right? And plus complex conjugate. And so if this equation is to be true mode by mode for every mode, right, then this has to be true that partial square A by partial T squared, this thing is equal to minus omega K squared A, which means that A of K X R, K of T, A of K of T, R K of T is AR of K e to the minus I omega K. By the way, you know for and this also, this comes from the fact that omega K is K. Okay? Because this is a massless field. Okay? So eventually you can write this A X T is sum over K R epsilon R A of K, AR of K, and this is all glorious, everything written down. Questions? So, for example, this is what I could think of what, for example, you guys should sort of brush up on. Most of you guys have already taken enough courses so that you know all of this. Okay. But if there are any issues with all of the things that I've mentioned here, by the way, I haven't mentioned, I forgot to mention, should have mentioned, perturbation theory. But I think that everybody's done that, both time independent and dependent perturbation theory. Okay. And so, at least first order. Anyhow, so yeah, I guess. So, any questions, guys? Okay. So now that I've mentioned everything that you need to know before the next class on Friday, let's talk about one more thing, one last thing. Very important. Can we move this class to oh, well, of course we cannot move this class to Thursday. Can we move this class to either 11 a.m. on Friday? Just the Friday class. I'm talking about just the Friday class. Can we move the Friday class to 11 a.m.?
मतलब अगर बच्चों को मसला नहीं
कोई भी बच्चा नहीं हाँ जी Is it okay? हाँ जी तुम तो बड़े खुश होते हो और किसी को कोई मतलब नहीं है आप नहीं हो. In the last class we discussed that everybody was okay with everybody had that slot free. So is there anybody else who has a problem with that? Because you guys are new, 1, 2, 3. You guys don't have a problem with that, right? No, I'm talking about Muzammil.
No, sir. I
Are you okay?
Tuesday.
Thursday को ये लोग नहीं कर सकते.
Tuesday.
The bulk of the class.
Friday को ही है free slot.
Friday को फिर. So we'll have our next class on Friday at 11 then.
इधर
वो अजनेत आपने आज अच्छे साथ से बात करके ना तो टाइम कोई वेन्यू जो है वो निकाल लेना और आज फिर वो आ जाओ मैं ऐड कर दूँ ताकि फिर उनको ईमेल कर दूँ. ठीक है? So let's meet on Friday.
Junaid bhai ji are. Junaid bhai, mine. MMP कर लेना MMP.